Hello everybody. This is my best webinar related to the reservoir characterization. Today I am talking about capillary pressure and saturation height modeling. As you know, the production performance directly depends on fluid saturations in the reservoir. That's why we need to know what's the fluid saturation vertically and aerially in the reservoir. For this, we need to know what's the capillary pressure and what are the effects on capillary pressure and how we use capillary pressure data for modeling the saturation height above free water level. Okay, first I would like to explain some key concepts related to the capillary pressure. What's capillary pressure? Capillary pressure is interaction and interface between two immiscible fluids. One fluid is wetting phase and another fluid is non-wetting phase. For a water-wet rock, the oil is non-wetting phase and the water is wetting phase. Okay, the capillary pressure, as we demonstrate with oil pressure minus water pressure. As you see in the figure, if we have one container, inside we have oil and water with a capillary tube. At the point A, the capillary pressure is 0. When the fluids rise up, at the point B, the capillary pressure will be oil pressure at point B minus water pressure at point B. And finally, we will have PC equal to 2 sigma cosine theta over R. The R is capillary tube radius, which in the power system is the power throat. The contact angle is the angle between the two immiscible fluids, oil and water, at the presence of a solid, and the sigma is the surface interfacial tension between solid and wetting phase fluid. Generally, we have two types of the reservoir rocks. The reservoir rocks naturally are water-wet rock or oil-wet rock. In water-wet rocks, the water coats surface of the grains in the pore system. Opposite, in oil-wet rocks, the oil coats surface of the grains in the pore system. Usually, the sandstone reservoirs are water-wet and mostly oil reservoir, and mostly carbonates are oil-wet rocks. The production performance of water-wet rocks are better than oil wet rocks. Okay, because we have interaction between the solid and wetting phase fluid, therefore the tension between the solid and fluid is called interfacial tension, shows with IFT. The contact angle is the angle between oil and water at solid surface. Generally, for water wet rocks, the contact angle is less than 90, usually between 0 and 70 degree, and for oil wet rocks the degree is greater than 90, between 110 and 180 degree. When we want to model the saturation height, we need to define the contact angle and surface tension at the fluid system for laboratory and reservoir conditions, the values. And you see in this table the values of cosine sigma, cosine theta, and sigma for different fluid systems. Can be air brine, can be oil brine, can be mercury air, air oil, oil brine, or gas brine. We have in most of the reference book and literatures this table. When we do the test in the laboratory, generally we produce two types of the PC curves. One drainage, the other imbibition. The drainage PC curve is non-wetting phase, fluid displays wetting phase. So non-wetting phase saturation increased. But opposite for drainage, the imbibition is wetting phase fluid displays non-wetting phase fluid, so wetting phase saturation increased. That's why the production performance of the water wet rocks are better than the oil wet rocks. We have some parameters have effects on capillary pressure measurements. The most important is pore size and pore size distribution. We know in reservoir the rock change by the rock types, and every rock type has its porosity and permeability and pore throat. That's why for each rock type the contact angle and the radius of curvature vary for each rock type, and that's very important effect, which the effect change the shape of the PC curve. For example, from top you see a very good rock with the coarse grains, which has good permeability and porosity. and the drainage curve is full shape of L. With reducing the rock quality, you see in the below figures the L shape change, and the curve is less L shape and move to the right side of the plot. And in the right figure, you see the drainage curves change based on rock porosity and permeability, which the smaller porosity and permeabilities related to the rocks move to the right side of the plot. When we start to measure the PC data, we have a point above the free water level, close to the water oil contact, which the oil started to entry in the rock. The pressure at this point is minimum pressure and is called entry pressure or threshold pressure. This figure shows the vertical distribution of the fluid in the rock, which we have different zones from top, which the saturation didn't reduce, water saturation didn't change. This is the zone we produce pure oil because of the water cannot produce due to capillary pressure. And this zone called irreducible water zone. And below the irreducible water zone, we have transition zone, which we produce both oil and water. And finally, we have a threshold pressure point, which the water oil contact located at this point. And if you feet below the water oil contact, we have a free water level, which the capillary pressure is equal 0 because only we have water as fluid in the rock. Capillary pressure data have a lot of applications. The most important is with capillary pressure data, we calculate reservoir original fluid saturations. And we can evaluate reservoir production performance. For optimal reservoir characterization and hydrocarbon production, we need to evaluate TC data. And the modeling saturation versus height give us vertical distribution of the fluids in the reservoir. Also, petrophysicists use the saturation height function for checking the log derived water saturation from logs above the transition zone. The calibration method is, as you see in the slide, from the left figure, we have PC curves for 4 different rock types. And at the right side, we have the saturation values from logs versus calculated porosity from logs. The trend of the curves in this plot should be the same as the trend of the PC curves. If there is no good trend, therefore we need to reevaluate the logs, change the evaluation parameters like clay volume, porosity, Archie parameters like M and N to achieve the good trend between these two plots. That's very important. We confer the accuracy of our calculated water saturation from the logs based on the PC data. Only the logs cannot resolve reservoir saturation problems solely because the estimated water saturation from the logs is based on the logging tool readings, which we have a lot of uncertainty with log data. These uncertainties are related to the borehole environment, including mud type inside the borehole, mud components, borehole actual diameter, washout effects on the log readings, and also other effects. For example, when we have oil-based mud or very fresh water mud in the borehole, the micro-resistivity tool doesn't work. Then, because of the mud type in the borehole, we don't have REPPCO measurements. Without REPPCO, we cannot correct the effective porosity for hydrocarbon effect, and also we cannot remove the invasion effect on deep resistivity. Determined water saturation from logs is depend on the M and N parameters we are using. When we don't have these data from the core, therefore we have to use a constant M and N value. This makes uncertainty and put effect on water saturation estimations, because we know in carbonates we have different rock types. Based on the rock type, the M cementation exponent and N saturation exponent change, and basically we should have formation resistivity factor and effective porosity from the core to plot and estimate M for different rock types. Then for each pore system, which can be a matrix pore system, fracture, or Wakley pore system, to generate an equation which the M vary with the porosity. Otherwise, we will overestimate the water saturation in fractures and underestimate in Wakley pore system. Also, the formation water salinity we use to calculate the formation water resistivity. If we don't have the data from laboratory measurements, this is another parameter affect the water saturation results. The free water level exactly cannot identify by resistivity log. That's why we need to model saturation height above free water level with using free water level from formation tester to achieve the right free water level depth. This is the slide shows the effect of Archie parameter M on water saturation when we calculate water saturation from the logs. In this figure, in y-axis we have M values, and x-axis the true water saturation over I cannot read, and you see the M effect on different porosities increase by reducing the rock type quality. This plot shows only a small error in M value. For example, here is 0.25. Then for 10 porosity rock, we will have error about 35% on water saturation. With reducing the rock quality, the M effect on SW increased, and in 1% rock, 1% porosity in the rock, the error increased to 80%. As you see, in carbonates, because we are working with low porosity rocks, that's why the M value effect will be high on the water saturation determinations. In the right figure, you see M versus porosity data from the core for one of the Middle East carbonates gas reservoir. You will see for dolomite, which the data are red points, and for limestone blue, we see, because we have good plug samples from all rock types, we can see different pore system in the plot. which you see for limestone. We have a lot of points which shows the rocky pore system, and most of the dolomite points are located in the value equal to 2, which the pore system is a matrix system. And you see both for limestone and dolomite rock types, the plug samples shows M value less than 2, which is related to the fractures. That's why you see for each pore system, the M will be vary and depends on the rock porosity. If we don't use this method in the log water saturation estimations, we will have big error in our SW values. For core planning and test methods, we have to keep in mind some issues. The capillary pressure test should plan for the wells which we know there are fluid contacts. That's why we don't go to plan capillary pressure program in the core for the wells are located in the crest of the reservoir. We need to have PC data from different parts of the reservoir, at least PC data for one well in the west and another in east, north and south. In this case, we can using the PC data of 4 wells which are located in different parts of the reservoir. We model a very good saturation versus height can be defined the vertical distribution of the fluids in the reservoir. The core plugs should be selected based on all available rock types in the reservoir. Otherwise, we cannot have full PC curves which can be defined the different rock types, drainage, PC curve. The test method we want to use, the test method should be selected based on reservoir rock lithology. And you will see in the next slide for which lithologies we use which methods. Also, that's very important to keep in mind. For the wells we plan capillary pressure data measurements, definitely formation repeat pressure test data also have to be recorded and planned in the core program, because for accurate saturation height model, we need to know exactly where is located the depth of free water level, and as you see, the most accurate depth point for free water level comes from pressure versus depth plot, which where the point is intercept of oil gradient and also water gradient. Generally, we have different methods, but the main methods are pulse plate, air mercury injection, and centrifuge. The pulse plate is measured in the laboratory and usually used for soft and unconsolidated rocks because we work with low pressure and give us very accurate results because the fluids we are using in the laboratory are the same fluids we have in the reservoir, which are brine and oil. The air mercury injection used for low porosity tight rocks, and we work with high pressure, which can be reached to 2000 psi, and there is a problem with this method, which injection at high pressures damage the surface of the core plug, and the effect we have to correct on PC data called closure effect. Centrifuge used for the rocks have a vacuum pore system and also shavy sand rocks. The pulse plate and centrifuge give both drainage and imbibition curves, but air mercury injection give us only drainage PC curve. Plug sample selection. What we want to use to select the depths for core samples, the best method we have to use is the FZI method. In this method, we calculate FZI per rock type using the hydraulic flow units, and the FZI directly shows the heterogeneity of the reservoir. And because we have to model saturation versus height based on the rock type, that's why we need to group the PC curves based on the FZI results. The procedure generally for measuring the PC in the laboratory is that the core sample cleaned and dried and saturated with brine and inserted in a core chamber several times, or injected into the sample and measure SW from volumetric readings. In every injection, we increase the pressure, and the injection of oil continued until sample fully saturated with oil and obtain a full PC curve for each rock type, and this take different times, which change by the test method. For air mercury injection is very fast, and for pulse plate need a long time to create PC curves. Because of the time limitation, I don't want to explain the test methods, and I continue the presentation with this slide, which for each method shows the PC curve which produced from the method and the time we need. For pulse plate, per pressure, we need between 3 and 4 days, and recommended is 10 days. For centrifuge is between 1 to 2 hours per pressure. Sorry, it's 24 hours. And for mercury injection is very fast, complete curve, and need time between 3 and 4 hours, and recommended 8 hours. Now we talk on the main subject, which we use capillary pressure data for modeling the saturation height based on rock types. I show an example here, which I used the petrophysical software to model the saturation height for a sandstone well. First, with using the special loader in the software, we load the PC data, plug saturation data, and for each depth we have these data. Also, we need to include the porosity and permeability values from the SCAD data. And after logging the data, we set up in the software the loaded and called the loaded PC data, permeability data, and also porosity data. Then we need to check the quality of the PC curves, and we create different plots which can see the quality of the PC curves on PC versus saturation plots. If we have pitfall data, we need to edit these data or eliminate from the calculations. And there is option in the software which allow to us to show the quality of the samples, which are bad or good. When we select the bad sample for any given depth, the software didn't use these data in the modeling, saturation height modeling. The main corrections we do on PC data are closure, stress, and capillary and clay-bound water corrections. The closure just we use for air mercury injection PC data, as I explained before, because the injected oil in high pressure damage the surface of the plug. We need to correct the PC data for closure effect. The porosity and permeability data we use should be overburden corrected, and also the permeability data have to be corrected for slippage, for gas slippage effect called Klinkenberg effect, and also for clay-bound water effect. We need to know the water salinity and also cation exchange capacity values from core. Then in the software we define what's our fluid system, oil water or gas water. With clicking on the type of the fluid system, the sigma and contact angle values for laboratory and reservoir conditions will be used based on the test method. And also we need to define the water density and the hydrocarbon density. Some functions are available for calculating water saturation from PC data, which are regression methods, Famir, Sling, J function, Johnson, power function, Foyle function, Scott, Harrison, and EOR method. Just because of time limitation, I will show an example which show us how we can use the J function for saturation height modeling. Also, we need a method which give us regression function. We can use different functions, which the most popular functions are hyperbola, lambda, and exponential. The Lagrange J function defined the formula used to calculate J function at laboratory condition and also reservoir condition. And you see the equations which use contact angle, interfacial tension, PC data, permeability, and porosity of the core. Okay, this slide shows which we assumed that we have only rock type in the reservoir, and then use all the PC curves without using grouping their curves based on the FZI, and you can see using the leverage J function method and the lambda regression function, we can estimate the relationship between the SW and J function. But actually, we know the reservoir rock change with rock types. That's why we need, for each rock type, we group the PC curves, and then using the discriminator define like this to group the PC curves based on the rock type using FZI, and then using the discriminator and defining the FZI values for each group to calculate the relationship between SW and J function for each rock type. And as you see, the FZI is calculated from rock quality index or normalized porosity. The RQI is calculated from this equation, which we use constant correction factor and also core porosity and permeability. In these figures, you see the flow units for different pore system and rock types. The relationship between permeability and porosity is changed. In this plot, which is RQI versus normalized porosity, we can calculate FZI where the curve for each flow unit intersect the y-axis at normalized porosity equal to 1. And in this table, you can see for the depths we have core samples calculated the FZI, also indicated the rock types. We can use this data for grouping and separating the PC curves to make different models, PC models, to calculate the saturation height above free water level based on the rock type. For example, in this slide you see a group of PC data which they have FZI between 2 and 4, and then we calculated the SW equation based on the J function, and the coefficients for A and B are estimated from the average J function. basically we need to use the free water level from formation pressure tester data to define the free water level exactly. If we don't have these data, we need to define an interval to the software which to find us the best fit for free water level. That's why, as I explained, for good model we need to have free water level from MDT, and we have to put in the core plan, in the plan. Otherwise, the free water level the program calculate will have uncertainty. And also in the software, we need to correct the IFT factor, and we use this equation to match the SW from logs with the SW calculated from the saturation height, and also finally we see good both SW curves match with the plug saturation measured at the laboratory. And finally we calculate and show the distribution of the saturation in the rock with using this plot, which the SW plotted versus height above free water level. And in this plot you see the transition, the irreducible water zone, transition zone, and then entry pressure point. Here you see matching of the log SW blue curve with the calculated SW from height, the red curve, which you see there are good match. This is an example from a sandstone reservoir. I worked on an offshore heavy oil well in western Venezuela, and you see good match at the intervals. We have hydrocarbon and we have good match with core permeability and calculated permeability from the logs based on the rock type, and also good match between the rock types from the core and the calculated rock types from the logs. And also in these tracks you see the uncertainty of the calculations for clay volume, water saturation, porosity, and permeability, which shows less than the uncertainty for each parameters we calculated is less than 1%, which means that this is a good job. And thank you so much for your attention, and also thank you so much for your time. And I would like you attend in the next webinar will be announced on LinkedIn.